Hello guys, and welcome back to class. We're jumping into some more algebraic simplifying today, and we're going to extend the tools in our toolbox. In the last unit we learned how to distribute and combine like terms. We're going to start multiplying some algebraic characters or some algebraic monomials today using the product rule. But first, let's start thinking about what we know about exponents and how they work. And this is a throwback a little bit. If this is Thursday, it's Throwback Thursday into the first unit, representing these things in exponential form along with an exponent. So go ahead and do these. See if you can represent these expressions exponentially alongside, and I'm going to do the same exact thing. And you've got 5 7s multiplying each other here. So hopefully you got 7 to the 1, 2, 3, 4, 5th power. An exponent says that that's how many times you use the factor that is the base in a multiplication problem. So it means 5 7s multiplying each other. This one, I've got a 5, and then I've got 1, 2, 3, 4, 5 G's multiplying each other. So that's 5, and then G to the 5th power. And if you remember, we had a fun little catchphrase. Exponents are all about that base. This 5 as an exponent only applies to the G. Does not apply to the 5. We do not have 5 5s multiplying each other. We have 5 G's. So it's 5G to the 5th. X times X times X times X is X to the 4th power. 1 over n times 1 over n times 1 over n is 1 over n to the 3rd power. In this case, I am going to need some parentheses because not only do I have 3 1s on the top multiplying, I have 3 n's on the bottom. So if I did not use those parentheses, it would be it would look only like the n, or sorry, only like the 1 is being stretched out to the 3rd power. And finally, I've got 3n times 3n times 3n times 3n. And once again, I'm going to need a little bit of parentheses here to represent this with an exponent. 3n in parentheses to the 1, 2, 3, 4th power. In this case, if I did not have those parentheses there and I wrote it as 3n to the 4th without parentheses, it would be deceiving because it would look like I only have 4 n's multiplying each other. And that's not the case. All right, in this case, it's out of order, but by the commutative property, I've got 3 8s multiplying each other. That's 8 to the 3rd, and then W to the 1, 2, 3, 3rd. So if you did it 8 to the 3rd, W to the 3rd, you're absolutely correct. But also, there's another way that I could do this. This is also an 8 and a W, since they both have the same exponent, is an 8 and a W in parentheses to the 3rd. These are mathematically the same. We're going to do a little bit of that down the road, and you're going to understand pretty intuitively why those are exactly the same, right? Let's go the other way real quick as we're warming up. See if you can stretch these out into multiplicative form. And knowing how to stretch expressions out into multiplicative form will help you a lot. Will help you a lot when you're algebraically simplifying. So if I'm stretching out 9 to the 4th x squared, that's 9 times 9 times 9 times 9 times x times x. This one's going to get tricky on you. This is the opposite of 8 squared. So if you think back to unit 1, that's going to be negative 1 times 8 times 8 times w times w times w. And why was it, where did this negative 1 come from? Well, remember, is the negative sign in parentheses and part of the base? And the answer is no. So it is basically the opposite of 8 squared. So the opposite of is negative 1 times 8 times 8. And then negative 9g to the 4th, if I were to stretch this out, that would be negative 9g times another power of negative 9g times another power of negative 9g times yet one more power of negative 9g. And you would be absolutely correct if you said, Mr. Cummings, is that 4 negative 9s multiplying each other and 4 g's multiplying each other? That is. If I were to keep stretching out, that would be absolutely correct. All right. Forward, onward. I'm going to skip these ones because I think we get the idea of stretching things out into multiplicative form or condensing them into exponential form, right? Let's move on to the full outcome of this lesson is to find the product of algebraic monomials that have powers in them. So the first example is n to the fourth times n to the second. And what I'm going to do is intuitively think about what I know about exponents to be able to simplify this expression. I'm multiplying n to the fourth times n to the second. Oops, I didn't mean to hit that. So what I would like to do is first, let's stretch this all out into multiplicative form. So if I have 4 n's multiplying each other times another 2 n's multiplying each other, that's n times n times n times n, that's n to the fourth right here, times 2 more n's. How many n's do you see there? Well, I've got 1, 2, 3, 4, 5, 6 n's multiplying each other. It would be, back in exponential form, it would be n to the sixth. All right. And now you might think about, can anyone think about a quicker way of getting from point A, the problem n to the fourth times n to the second, to the answer n to the sixth? And if you've got it, just hold on to that. And we're gonna go on, and I think that you're going to use your knowledge to be able to synthesize the rule here on the next slide. Okay, so can you find a quicker way? The quicker way would be the product rule that says you add the powers of any like bases in a multiplication problem. So the product rule of algebraic multiplying says, where's my highlighter? Here we go. Says that we are going to add the powers of any like bases to simplify any multiplication problem. So let's go back to that one. If you add n to the fourth and n to the second, that's a power of n times another power of n. When you're multiplying those two powers together, they do not have to be like terms. You can multiply anything. Voila, it ends up being n to the 1, 2, 3, 4, 5, 6 power, 4 plus 2. Right? So let's try this with eights. If I were to stretch out a whole bunch of eights, and yes, the question I usually get on a problem like this is, can we just put this in the calculator and hit enter? Yeah, you could. But if you know anything about exponents, 8 to the 12 is already going to max out your calculator. It's going to give you something in scientific notation, if not simply overflow your calculator. So let's just condense this with an exponent. So if I can do this rule with x's or n's, I can do this with eights as well. So 8 to the fourth times 8 to the 12th. If I were to stretch this out, that would be 1, 2, 3, 4 eights multiplying each other, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 eights multiplying each other. So quickly using the product rule, that would be 8 to the 4 plus 12 is 16. That would be 16 powers of 8 all multiplying each other. All right? Now, this is kind of getting into the meat of it here. 4x squared times 3x to the fifth. 4x squared times 3x to the fifth. Well, the commutative property says that I'm allowed to multiply the coefficients 4 times 3 together out of order. 4 times 3 is 12. Now, how many x's do I have multiplying here? That's 2 factors of x. And how many x's do I have multiplying here? 5 factors of x. If I were to stretch that out, that would be 2 plus 5. That is 7 factors of x total. So there you have it. The product rule says to make things quicker for algebraic multiplying, I'm going to add the powers of any like bases. Like bases mean they have to have an x or an a or something like that. Okay, so why don't you practice these? See if you can come up with the same answers that I do. All right, so on the first example, you've got 9 times 4 is 36. X to the fifth times one more x is actually 6 x's in this multiplication problem. And then you've got the factor of m2. You're adding the powers of like bases. And yeah, if you didn't pick up on this, if the number does not have any exponent, its exponent is really 1. That's x to the first power, whether it says it or not. 4n times 5n. We're not adding here. This is multiplying. So we go 4 times 5 out of order by the commutative property is 20. And n times n is n to the square, n to the second power. And 6t cubed times xt to the fifth. 6t cubed times xt to the fifth. Interesting. All right. So do these parentheses matter? That's what I want to ask you. Do these parentheses matter? And the answer is no. By what property? The associative property says that these parentheses don't matter because the operation is all multiplying. So I'm going to go that's 6 times t to the 1, 2, 3, 4, 5, 6, 7, 8. T to the 8th power. 3 plus 5 is 8. And then the x. If you had this as 6 xt to the 8th as well by the commutative property, that is the same thing. So we are using our properties very heavily anytime that we algebraic simplify. It justifies what we can do and what we cannot do. All right. Try these last 3 on your own, and that's where we are going to stop for today. All right, so 9 to the negative 8 times 9 to the 14. 9 to the negative 8 times 9 to the 14. And that is by the product rule that says I'm going to add the exponents together. So very simply, 9 to the 14 plus negative 8 is 6. And if you don't understand negative exponents yet, that's okay. Just note that they're negative, and we're going to follow this rule, and we'll deal with negative exponents in a deeper level later. But 14 plus negative 8 is 6. That's 9 to the 6th. And usually the question that people ask, this is people thinking about the question, a very common misconception here is, why is it not 81 to the 6th power? Why is it not 81 to the 6th power, Mr. Cummings? On the last ones, you multiplied the 4 and the 5 together to get 20. In this case, you did not multiply, Mr. Cummings. You did not multiply 9 times 9 to make 81. And why not? Well, in this case, the 9 is not what you call a coefficient of another number. The 9 itself is the base. It would say, how many 9s do you have here? So if I were to stretch this out, and we're going to come up with the catchphrase, when in doubt, stretch it out. And excuse me, but I do not want to stretch out 14 9s right now. I can do that at your desk if you really have this problem. But 14 9s, and this is basically saying take away 8 of those 9s. In a multiplication problem, you've got 14 9s there. Take away 8 of those 9s. How many 9s do you have? You would have, well, 14 minus 8 is 6 factors of that 9. That's why it is not 81 to the 6th power. You do not have any 81s in the math problem. Do you see an 81? Nope. Do you see an 81? Nope. Okay. You just see simply a bunch of 9s. What about these g's? I've got 2 times g to the 1, 2, 3, 4, 5, 6, 7, 8, 9 minus 4 should give me 5. It's going to be 2g to the 5 power. Let me get out the eraser. Correct that one. Little eraser. So you should have gotten 2 times g to the 5th for that answer there. And then the last problem. Do the parentheses matter? No. What property? Associative property. So I'm going to go 4 times negative 5 is negative 20. F times f to the negative 4th. Well, you've got 1f. But then you're dividing by 4, which is what that means. We'll get more into that later. I'm going to have f to the 1 plus negative 4 is negative 3. And then the g times the x, they're just simply going to tag along. So you get negative 20, f to the negative 3rd, gx. So there you have it. That is the product rule of multiplication that states, if you've got a whole bunch of bases with different exponents, like these g's here, you can just simply add the exponents together. All right? Or when in doubt, stretch it out. Do it the slow way if you need to. See you later.